If you want to win a game of Guess Who, your first move is usually to ask a question that cuts the board in half. A machine learning decision tree operates on that exact same logic. It evaluates the data and asks the most informative question first to eliminate the maximum number of options. This diagram compares two possible starting questions. Asking, "Is it a man?" creates two large, balanced groups. That is a highly informative split. But asking if the person wears glasses isolates only one character, which leaves you with an uneven, largely unhelpful group for your next turn. The underlying algorithm's entire objective is to sequence its questions from most to least informative. By continually prioritizing balanced splits, it minimizes the total number of questions needed to reach an answer. Decision trees automate this process of elimination, using mathematical optimization to find the sequence of questions that yields the most information. Looking at this tree anatomy diagram, we can see the physical structure of that elimination process. The entire training dataset enters at the top through the root node. It divides into smaller subsets at the internal split nodes, and the process terminates at the leaf nodes, which contain the final predictions. If we zoom into a single node, we find 4 precise metrics. First is the split condition, which is the rule dividing the data. Second is the Gini impurity, measuring how mixed the categories currently are. Third is the total number of samples that reached this node. And fourth is the value, showing the exact class breakdown of those samples. When the data finally reaches a terminal leaf node, the model makes its final output based on a simple majority vote. Whichever class has the highest count in the value array becomes the prediction. This node-by-node architecture ensures that every individual prediction is traceable and interpretable by humans. To find those split conditions, the model relies on the CART training algorithm. The tree doesn't guess, it performs a greedy search, evaluating all possible splits across all features simultaneously. The engine driving this search is the cost function, labeled J. The algorithm's only goal during training is to find the specific feature and threshold that minimizes this equation. This formula calculates a weighted average of impurity. It multiplies the Gini impurity score of the left and right child nodes by the fraction of samples they contain. This ensures the algorithm balances the size of the new groups against how pure they are. This 2D scatter plot visually demonstrates that mathematical splitting. Every time the algorithm minimizes the cost function, it draws a strict axis-aligned line through the data, partitioning the space into smaller rectangular regions. This mathematically aggressive pursuit of pure nodes forces the data into increasingly homogeneous subsets, which is exactly what gives the tree its predictive accuracy. If you need to predict continuous numbers instead of categories, CART pivots to decision tree regression. To do this, it simply swaps out Gini impurity for mean squared error. Looking at this regression graph, you'll notice it doesn't generate a smooth curve. Because every leaf node predicts the exact mean average of the data points within its specific region, the resulting prediction line looks like a series of flat steps. Let's test this logic. Given a starting node perfectly mixed with 50A and 50B samples, which split will CART choose? Option A, which creates two 50-50 nodes, or option B, which creates one mostly pure node and one mixed node? The algorithm chooses split B. Option A reduces zero impurity. Split B successfully isolates a highly pure subset, which mathematically reduces the overall cost function. Whether classifying categories or calculating numerical averages, the core behavior is identical, a greedy, step-by-step reduction of error. But that greedy reduction has a cost. If left unconstrained, the tree will continue splitting until every leaf has exactly one sample. Looking at this diagram, you can see the result, an overfitted tree that has perfectly memorized the random noise of the training data. This creates high variance. Because splits are tied strictly to specific data, tiny changes radically nucleate the final tree. Furthermore, trees only cut horizontally or vertically. Confronted with rotated data, they must draw complex, inefficient staircase boundaries to separate classes. The aggressive pursuit of pure subsets makes raw trees highly effective at learning, but also vulnerable to memorizing noise instead of signal. To defend against overfitting, engineers use regularization. By setting strict parameters before training begins, like capping the maximum depth of the tree or requiring a minimum number of samples in a leaf, we force the tree to stop growing before it learns the noise. We can also use a reactive strategy called cost-complexity pruning. Here, the tree is allowed to overfit completely. Then, we evaluate the full tree using cross-validation to see which branches are useful. By applying a complexity penalty called alpha, the algorithm aggressively snips away lower branches that don't significantly improve accuracy, leaving only the most robust splits. Decision trees use the CART algorithm to ask the best questions and optimize impurity, but ultimately they rely on human-imposed constraints to maintain their structure and generalize effectively.